Good morning, everyone. Can you see my screen? That's great. Just let's give a couple minutes more, but I guess all of us, we are already connected.
Good morning.
Good morning, Dr. Chen.
Sorry, I was late, perhaps for 1 or 2 minutes. So are we still waiting?
Yes, I think everyone is here now, so I was just about to start.
Oh, it's Furkan is also here. Great. So Furkan and Jairo, maybe you both turn. I suggest everybody turn the video on so we take a group picture. Okay. So could you do that, guys? So I think this is a good idea. So we are going to do this one in the future for the beginning of the class. We do group picture. Take this as lab attendance, okay? So yeah, thank you for turning on your video. Could you turn on the video? Let me type a message for everybody. So we have 3 hours here. We are going to have lots of fun. So the reason I'm here, I'm just trying to show my support. Okay. Actually, this is Jairo's session. Is this Jairo's session? Afternoon or in the afternoon is Furkan's session, right?
Yes.
Okay. So please show your video. Okay. Show your video. I can't turn on my camera. I just have to switch devices. But probably it's okay. One of the important things is you need to turn your real name instead of using a very special type of name. We don't know that's you. So cool. Cool. Thank you. Thank you. Thank you. Garrett Jones. Garrett Johnson. Okay. Okay. So the reason I call you because I just graduated a student called Garrett Jones, and then I saw, oh, why this name is still here? Johnson. Okay, it's different. Okay. There's some names very familiar to me, like Kevin Lemus. Oh, you have two. You have two copies of yourself, Kevin. No, don't hear you. You are muted. All right. So, Harold, are you ready to take
Sure.
to take a group photo together with your ME142Sp21 So I want to say that this is an unforgettable, once in a life experience. We are learning mechatronics lab through the distant. Then you can feel proud of yourself to explain to your future kids or grandsons that you learn mechatronics, and tell them that the professors and TAs work hard and figure out something called a digital twin. And so it will be fun, okay? So it's a great journey, and So attendance is very important, okay? So I'm going to shut up and I turn my video off. So let the journey begin. All right, bye-bye.
Everyone can see my screen, my share screen right now? Okay, that's really good. Everyone is listening also, I guess. So please be welcome to ME142 Lab, in this case, offer for Spring 2021. I mean, my name is Jairo Viola. I will be your TA for this first session of the TA. The other TA is also connected, Forkan Guk. He's the TA for the other two sections. Together with Dr. Chen, we're going to be with you during this 16 weeks journey of mechatronics. This is like, as Dr. Chen said, like once in life experience. All the course will be offered totally remote. And it means that we have some challenges to address in the sense that we are going to use new tools that we are, I mean, that for sure will be like the first time, at least for ME142, that we are going to use in our lab for, for enhance or empower the teaching, even without the possibility of accessing directly through the hardware, as we do on previous semesters. Okay. So this is like an introduction of the course. What are our expectations of the course and how we are going to how we are going to work in multiple topics and cover mechatronics in remote learning. What are our lab expectations? How to complete the reports? Some general guidelines about report formatting and lab management. And finally, some questions about that you could have, Q&A that you could have in this case. Okay, so this is the lab offer that we made last year during 2020 spring. I mean, the beginning of coronavirus. In this case, our original lab plan introduced a strong hardware-based laboratory where you will be was able to build a lot of circuits and build by yourself mechatronic systems, model systems, and control those systems using real hardware. Let me keep my window. Yeah. Okay. So in this case, for ME1 spring semester of ME142, the first part was hardware-based, totally hardware-based. However, we have to switch to remote, and we switch into the MAD methodology, modeling, analysis, and design. That is the basic methodology that we can follow for controller design and develop control applications. That is totally applicable in this case to mechatronic systems. In this case, for last year, our main support was the CTMS website. We're going to see this website in more details, and also will be a really great tool for us during this semester in order to learn all the fundamentals, not only for mechatronics, but also for control systems. That is one of the fundamental parts of mechatronics. So that was like the offer partial remote on 2020 spring. Today, we're going to start a totally remote ME142 laboratory for 2021 semester year. In In this case, the lab is composed by 10 practices. The first one is something about ethics and safety on engineering and mechatronics. Lab 2 and 3 will be focused especially on Matlab and Simulink for mechatronics and how to use those tools in order to create our own models for multiple modeling and analysis of different systems. Matlab and Simulink is huge, and for controls is like it's like the right way to go to if you want to design really good control tools and perform really good mechatronic analysis. So we are going to focus during these two labs in how to use Matlab and Simulink for mechatronic applications. We are going from scratch, so don't worry if you are not too familiar with Matlab. We are going to start from scratch in order that you can catch up all the details to develop systems. Then Lab 4 and 5 will be based on digital signal processing. This is another fundamental component of mechatronic systems. In this case, it's more based on filtering, signal filtering, types of signals, Fourier transformation, all the basics that you need for understand better the signal processing part on mechatronics. Lab 6, we are going to work something called multiphysics modeling of mechatronics. This multiphysics is important in the sense that right now we are not close to hardware, but using multiphysics tools, we can approach and generate complete simulation environments that replicates our physical hardware. So we will have one lab dedicated to the tool Simscape of Matlab in order that you can see how Simscape works and use that tool in order to develop more complex and robust simulation models. I mean, to get this closer to hardware experience. The Lab 7, this is a foundation of system identification. We're going to see that this is one of the mandatory steps on mechatronics and control design. We're going to have a taste of system identification that you can catch up what is system ID and how it's useful inside all our mechatronic applications. The main part of the lab is Lab 8, Digital Twin for Mechatronic Systems. After get all the foundations on Matlab Simulink tools, simulation, and digital signal processing, we are going to introduce for first time and in the case of ME142 also first time, the digital twin, in this case, apply it for mechatronic system and applications. Digital twin is a really broad concept that covers all the areas and is right now is being applied to all the industry and all the different processes that you can imagine, not only like mechatronic process, but all kind of systems, biological, social systems, and corporative systems. I mean, is everywhere. So in that sense, digital twin will be our best tool in this case to develop this remote laboratory. That sense, digital twin, we're going to go deep during this lab, but digital twin is a virtual representation of some physical system with the most possible detail. And also it has multiple features like real-time interaction with and updating with data that comes directly from the system. And it involves many things like data analytics and real-time signal processing. We're going to try to focus more on mechatronics, but this digital twin is something that is breaking changes on something that is called on industry digital transformation, which is like one of the first pieces towards industry 4.0. Not only business that offers some, I don't know, building elevators, but also that provide value to their products through services and digital technologies like data analytics, machine learning. And digital twin is one of those technologies that enable this digital transformation. So this will be one of our fundamental pieces for this course. Then we are going to focus on the MAD methodology, modeling, analysis, and design for mechatronic applications. In this case, this will cover the steps of model a system, design, analyze the system. I mean, stability, time response, all the features that could involve any control system, and design, controller design. In this case, we're going through some of the most popular controllers. In this case, PID controllers. We're going through this kind of control schemes, how to design these controls for any system. That will be the main idea. And we're going to support all our MAD methodology using the digital twin. And of course, all the previous skills that we are going to be acquiring during the semester. At the end, we will have a final project for the course. This final project is basically, we're going to use the MAD methodology to model a mechatronic system and build a web application and develop a web application using a new feature of Matlab called Matlab Web App Designer, which basically allow us to have like our own application, our own user interface, and we can share this interface directly through the internet, and we can make this access by anyone. So that will be our final project: develop a full mechatronic application following the MAD methodology, and develop that web application in order to have like to show how we can do our work, in this case, into a globalized environment, more than just like local control, where we can extend all those concepts. This is the structure for the remote lab. I mean, this was last week, no lab. This is week 2, where we start the laboratory. This is our today practice: lab safety and engineering ethics, robotic and electronic safety, electrical practices and engineering. This is the due dates for all the labs that we will have. Then next 2 weeks will be Matlab Simulink for mechatronics and control 1 and 2. Signal processing using Matlab Simulink will be the next practices. Then multiphysics simulation using Synscape, foundations of system ID, digital twin for mechatronic systems. Then week 10 is the spring break. So there's no lab during spring break. After spring break, we will have the MAD labs. The first one, position and velocity PID controller design, and MAD for nonlinear systems, linearized inverted pendulum system. This will be one special application where we are going to deal with a more complex mechatronic system. That will be pretty interesting in this case. The last 4 weeks of the course, we are going basically to work on the final project. On the first of those weeks, we are going to show you a sample case of the final project that we built on the Mesa Lab during the last months. And then based on this sample project, you are going to work directly on your project. Basically, you will have to develop a presentation, a recorded voice presentation, plus some final report, and of course, the web application development. That will be your deliverables for the last 4 weeks. The deadline for the final project is May 7th. So this is all our schedule. This lab is really intensive. So considering that we have to cover multiple topics in some period of time, so we will be really lab intensive lab. However, all the labs will have methodology, and you can follow all the steps on each laboratory in order to develop those skills with Matlab Simulink and go and scale more and more into digital twin. That is like our main goal, and develop the web application for mechatronic system. This is like an overview of all our practices. In this case, this is like the learning outcomes for each one. The first one is like introduce the basic of safety and ethical practices on mechatronic and professional career in general. Those are some teaching resources from Matlab website, and the ethics seminar by Professor Michael Louis of University of Illinois. So this will be our first lab today after this presentation. In lab 2, we are going to start working with Matlab Simulink. In this case, we are going to use the CTMS website. This is control tutorials for Matlab and Simulink. The link in the bottom is the link to this website. You can find multiple tutorials on Matlab Simulink for multiple systems, from a really simple one to really complex. So this will be one of our major tools for learning mechatronics during this spring. Some of the outcomes basically introduce Matlab as fundamental tool for mechatronic and control systems, and acquiring the basic simulation skills for using Matlab Simulink. That will be some of our first goals, using in this case RC circuit and RLC circuit as initial systems. All of you take circuit theory, so you should be familiar with RC and RLC circuit. So this will be our first step. Then lab 3 is the second part of fundamentals of mechatronic and control system. In this case, we're going more into the comprehension of the type of systems, first order and second order system, which are the more important or the fundamental blocks in model and mechatronics application analysis. Recognize if the system is stable, unstable, critically stable. Also recognize properties on the time response of the system, like what is the setting time, what is overshoot, what is rising time, what is time constant of your system. So in that sense, we're going to have a lab where we're going to be able to recognize all these features into a first and second order system. And of course, using Matlab Simulink to replicate these types of systems, and also evaluate the systems in the presence of different inputs like step, impulse, or sinusoidal inputs. So we will have a comprehensive view of modeling and simulation with Matlab during these first two labs. Something important is that we're going to, during all the mechatronic course, it's important to understand ODEs, ordinary differential equations, and that you get familiar with Laplace transform, and that you get familiar with Laplace transformation. That's another important thing. With the progress of the course, you are going to be more comfortable with Laplace transformation and ODEs. But if you already see the topics before, try to refresh. That will help you a lot, not only for the lab, but also for the lecture. That will be really, really valuable in this course. The lab 4, we are going to work about filters. Filters is really important part of mechatronic systems because help us to improve the quality of the signals that we are acquiring, for example, from a sensor. If the sensor has a lot of noise, we can use different types of filter in order to remove as much as possible that noise and have clear measurements, and using that measurements perform a better control, better analytics, and better understanding of our system. This is some examples of filters: high pass, low pass, band pass filter. Also, there are two tools that are important for us in mechatronics. One is the Fourier transformation, and the other one is body plot, body diagram. So we are going to go, in this case, how to calculate the Fourier transformation and the body diagrams using Matlab Simulink, and also how to create, which are these type of filters and how we can create those filters using Simulink, and basically learn how to design filters that will help us to improve our noise and performance sometimes for processing the data input into our model or our application. So this will be like our lab 4. On the lab 5, we're going to have some real action, if we can call it that way. In this case, we are going to perform some digital filters, the same like low pass, high pass, as we mentioned before. But we're going to use audio signals using the microphone of your computers. In that sense, we are going to acquire the signal, our voice signal, and then we are going to apply some digital filtering in order to see how our voice reacts in front of different filters. There are more, this is a really exciting topic because we can see some effects like modulation, attenuation of our voice components. So that's, that's quite interesting. And also we are trying to cover in somehow the digital signal processing. Considering that most of the, for example, when in this moment, while we attend this lecture, our computer is performing the real-time digital signal processing, listening our voice and transforming the voice using Fourier transformation and sending the information through the web, and then your computers or devices perform the inverse operation in order that you can listen to my words. So everything is do real time based on these digital signal processing tools. So will be pretty interesting to cover these topics. Then we are going to lab 6. In this case, the lab 6 will be advanced multiphysical system simulation using Syncscape. We're going to acquire basic skills for performing multiphysics simulation. Multiphysics simulation involves many things like electrical, thermal, fluid, multibody. We have multiple multiphysics simulation. In this case, Matlab Syncscape has a comprehensive set of tools that allow us to do all those simulations with really great accuracy. And in that sense, we can represent our physical systems using the Syncscape, even without having the physical system. For example, robotic manipulators. Sometimes a robotic manipulator, having one in real life, could be expensive or could take a lot of time to developing. So we can build multi-body simulation models first in order to design our manipulator, and then get the manipulator, or if we want to understand or try different controls, we can build a multi-physics model that represent our physical system, and in that sense, test in the computer first before testing on the real system. That's good because that will reduce the time of developing algorithms, that will reduce the risk for us if we perform some bad operation on the robot, and if if we made something wrong, maybe the robot can be damaged somehow. So in that sense, using this multi-body simulation, we can replicate as much as we can, and in that sense, boost our developing times. Also, we have like electrical part. In this case, this is like operational amplifier, op amps. So we can also simulate that with Matlab Syncscape. So we're going to cover some electrical models and also mechanical models. Of course, building these big robotic system that takes time. And of course, we're not going to build a whole robotic system in one lab session, but we're going to be close to some of these mechanical models also. So that's the main idea of the Scenescape, start to interact or build our own models, considering that right now we don't have like hardware access to perform simulations and to run real experiments. That's the point. So we're going to use ultra detailed simulation models that we can build by ourselves using tools that are common, I mean, for Matlab and also accepted by industry. So this is something really important. Then we're going through system identification. The system identification is a huge topic that could cover courses of graduate, at undergraduate level. It's huge, but the main idea with this lab is give you a hint of system identification, that you understand why this is valuable when we have a real system and we want to get a model of that system. That's the main idea of system identification. If I have something physical and I have some input and output data sets, I can take that data sets and somehow find a model or representation that represents the behavior of the system. That's the main idea of the system identification. That model could be a simple model or a really complex one. It depends of the complexity of the system and the quality of the data and multiple factors that we could have. But if we can have a model that describe our system dynamics, we can start to developing controllers. And in that sense, we can improve our design, not just like trial and error, tuning of a machine, but if we have a model, we can understand some of those properties that we already mentioned earlier on the talk, like setting time, time constant, overshoot. If we can visualize all these features and know how our system behaves, we have a really a lot of way gain in order to perform better simulation, to perform better control and better mechatronic practices. So this is something that is important in this case. Our main tool for system identification will be the System ID toolbox of Matlab. Has a comprehensive review of all the multiple identification algorithms and is user-friendly for us. So we can focus on what we care, that is the system ID. Then Lab 8, we are going to introduce the digital twin for mechatronic systems. In this case, we're going to understand the foundations of digital twin and its importance toward industrial digital transformation. This lab come at this point because we need all these multi-physics tools and Matlab and Simulink understanding and knowledge before dealing with digital twins. In this case, we are going to use the digital twin to replicate realistic models that we have. In this case, on the MESA lab, we are going to replicate those models using the digital twin to create as closer as we can models of our physical systems. In this case, we are going to follow this methodological framework for developing digital twins. This framework is one of the works that we performed since last year, and we are continuously improving on MESA Lab. This is the first time that we are going to apply the methodological framework for developing digital twin applications on ME142. So that will be really exciting to see how this is going to work. Our main support will be Matlab Simulink and of course Scenescape. There are some papers here on the archive. If you want to read more about the digital twin, you can go through those links and see all and read and understand more the idea of what is digital twin, this framework, and some applications. So this will be our lab 8. Then our lab 9, we're going to develop now, I mean, at this point of the, not only for the lab and also for the course, the idea of closed loop control will be introduced. So in that sense, at this time, we are ready, after we understand in the MAD methodology, the steps of modeling and analysis, we are ready to design controllers. So in this case, in this lab, we are going to be supported by digital twin, and we are going to design controllers for position and velocity, in this case for a DC motor system. That's like, I mean, that's like will be the first lab where we are going to understand and put together all the things that we will be learning through the semester and also through the lecture. So we're going to build our digital twin, get models of the system, design our PID controller, and test that controller in the presence of multiple things like disturbance, noise, set point changes. We can make several tests in that at this point, and also perform all the closed loop idea. So that's the main point of this position and velocity control lab. Summarize all the knowledge that we already acquired during the lab. Finally, this lab, we are going to a more complex system. This is like inverted pendulum. The cart inverted pendulum, as you can see here, is one of the benchmark problems in control engineering in general terms. This problem is, I mean, could be as much complex as we want. If we work directly using nonlinear models, we are not going through nonlinear models. We are going to obtain a linearized model of this inverted pendulum system. And based on this linearized model, where we can design controllers and apply all the framework that we have. Why we are going through a nonlinear model? Because on real life, most of the systems that you will find on industry or during your work are for sure non-linear. So if we can linearize or get some model for certain operation point, that is like the case of this cart pendulum system, that will be like keep straight the pendulum. As we bounce the cart, the pendulum should keep straight. That straight point will be our operation point, our reference to keep working. So we're going to use this problem to get in a better way this concept. So this will be, as you can see, is really intensive lab practice at this point. The final project, basically we're going to develop a web application. This web application is basically a mechatronic system that is built using Matlab Simulink and Synscape. This system, we're going to deploy a user interface, which we can interact with the system and modify parameters. And this application is designed in order to be available, online. I mean, if we just join to web browser to some URL, you can access the application. I'm going to put this video. This is an example of the web application. This is with a really simple system in this case. This is with a really simple in this case. As you can see, this is the spring damper, one of the benchmark mechanical systems. This is the position, velocity, the input signal. As you can see, we are interacting with all the tools. This web interface is developed using the Matlab App Designer. This App Designer is one of the features of Matlab for building user graphical interface, or GUIs. But if you see the top of the screen, this application is running directly from my browser. It's not running from Matlab. So this will be our main or final goal. Get an application like this, where we can modify parameters like controller parameters, model parameters, and we can simulate the response of our system and run this interface directly from the web browser. In this case, this is just a local test, but we can, I mean, we have a computer on the lab where we can put all these applications, and the applications can be available online for access to anyone directly through the internet. So this, I mean, this is like a hint of how will be our final project. We're going to show you a sample project much complex than this in order that you can see how to perform your own application. In this case, also we have like all the details, but the details for the specific details for the project we are going to provide you after the spring break once we go far on the course. So all the details about deliverables and everything will be released at that time. Okay, let's continue. Lab report formatting. This apply from lab 2 and beyond, not for this week lab, from next week lab. Basically, this year we are going to ask you to use the IEEE format for making the reports. What's the reason of using IEEE format? It's a really common format in engineering to present your results. This is like 2 columns Times New Roman 10 template or example of document. The main idea is 3 pages, length minimum, maximum 8 pages, built as self-contained reports. There are some important things related to the IEEE format, like caption of the figures, caption of the tables, use of images. Basically, all your images, all your tables should have a caption that describes briefly which it has. Let me just, this is an example that is already available on the CAD courses on the lab folder. This is an example, an example template of IEEE double column report. All the sections that we expect of the for each report are here, like an introduction, part 1, the system modeling, for example, in this case is the cruise control example for this vehicle. All the modeling graphs, you see that each graph has its own caption. All figures should have that one. Controller, equations, okay, figures, try to keep figures clear, some conclusions. This is an example of lab report in IEEE double column format. You can watch, you can download and use for all your lab reports the same template. That's the main idea for this lab. Follow all these, follow the steps, follow the steps here on the report format to make your own reports. Of course, will be different considering that in this case this is like cruise control, and your labs will have different applications. So, but that's like the main template that we expect that you follow. Between 3 and 6 pages is okay. Maximum 8 pages, in order to keep like the report as self-contained as possible. Okay. One of the most important parts, grading. All our weekly assignments, in this case, what it related to lab reports, is, I mean, has the 80% of the grade of the overall lab. 80%, the final project will have like is the 20% of the final grade of the whole lab. The laboratory inside the mechatronic course is equivalent to 30% of the course. So it's important that you put efforts on the course in this case. So that's really, really important. Some requirements: lab reports, IEEE format, PDF submission only. Template and sample report is available on CAT courses. If in some practice we ask you to generate some extra file like a video or some animation or something, you should also submit those as additional files to your submission. But that's not always will be the case. There are some specific labs where we are going to request, like, for example, an animation or some simulation model or some short video that shows the result. In this case, no late submission policy will be applied. You will have almost 2 weeks per each lab to deliver the final report. In that sense, each week you will have you have time up to Friday of next week to submit the final report. Lab attendance is mandatory. Attendance will be taken during the session, not necessarily at the beginning. But yeah, we are going to. But this semester, attendance will be mandatory for all the lab sessions. The labs, the main idea with the labs, all the labs will be released on Sunday night. And in that sense, all of you have like the same time to work on the lab. Most of the labs will have a tutorial session, a tutorial video session. We encourage you to see the tutorial video before coming to the lab, because that will help you to improve your performance during it. So that will be how, in this case, the lab will work. The lab will be released on Sundays, and with the practice and with the task and the tutorial. That will be like the main idea from this Sunday, and so on for the following practices of the course. If you have any questions, please, you can make any questions that you have. You can use the chat box if you have any questions about the course. Or something that you may want to ask. You just need to mute your mic. Want to ask something? I have one question. Will all labs be live on Zoom? Yes, I will be here for the 3 hours that takes the lab. We'll be here from, for this session, for example, will be from 9 to 12. And the other sessions, the corresponding schedules. Essentially, we're going to provide some guidelines at the some tutorial also at the beginning of the lab, and then you are going to work during the remaining 3 hours on the lab assignment, and also Furkan in his sessions and myself in this session. In this session, you can ask anytime. So as Dr. Chen mentioned here on the chat box, you work under camera for 3-hour lab, and you can ask questions anytime. The main idea is like keep the lab as if we were on the physical space. So if you have questions, you just write on the chat box, or you can, yeah, let's do it this way. You type on the chat box and we can start a discussion if there is some specific question. So I guess it's try to keep as much similar as we can with the real lab. Any other question? Okay. Any other? Again, this is a very lab intensive course, so you will have to spend some time to get the results of the labs. So in that sense, you will have to work harder for the lab and the lecture. So this is like, this will be our coursework for this spring semester. No more questions?
So for this week's labs report, can you explain what we have to do?
Yes, you will. I mean, you will have all specific tasks to do. I mean, what you will have specific steps like do this, then this, then this. Will be really specific on which task you have to perform at each lab. Okay. See. All right. So if you have more questions, please, if you have more questions or you need to, I mean, we have some predefined office hours on Wednesday and Friday. But if for any reason you need an additional office hour, you can, I mean, we can arrange one office hour by email, appointment by email, but try to use as much as you can the space on Wednesday and Friday. So that's a recommendation in that sense. Okay. Let me just go in this way. Good. Okay, this is our first lab today. The lab is called Mechatronics Safety and Ethical Practices on Engineering. The main objective is introducing you to some basic good safety and ethical practices, not only for mechatronics, but also for your professional career. In this case, for today's lab, we will have as required work. The first part, you are going to attend our first safety guidelines lecture. I mean, next to this explanation. In that sense, you will going to write down the most relevant guidelines for mechatronics, safety guidelines, and then you are going to introduce yourself at least 5 new guidelines for best mechatronic practices. We're going to mention some of them, but you should add a little bit more. And the second part, you should go through the Professor Michael Louis Ethics on Engineering Lectures seminar. Let me just go here. This is the Matlab website. At the bottom of the website, you will find the Professional Ethics in Engineering modules. Here you can find all the lectures. These lectures are really, there are 10 lectures, but each lecture takes like 8 minutes. So it's not too long. There are not too long lectures about ethics on engineering. You are going to watch the lectures and summarize the concept of ethics on engineering and its application into mechatronics. You are going to write as an essay, maximum 2 pages, minimum 1 page, with maximum 3 external references in addition to Professor Louis talks. All the essays will be compiled by the TAs, and we are going to create like a compilation of all your talks about ethics on mechatronics for this lab one. That will be the required work for today's lab and for today's lab. Okay, so let's go here to, okay, why is not? Okay, now is the the presentation. So let's begin with this safety guidelines for mechatronic experimentation. Into a real environment, we will, I mean, as mechatronic engineers, we will find multiple, we will going to work with multiple tools. For one side, we have like microelectronic and circuits, microcontrollers, sensors, actuators. But also in many cases, we will have mechanical parts, like if we work with robotic systems, or if we work with flow, level, temperature systems, we have many mechanical components. And also, of course, we're going to work with electricity. And sometimes this electricity is low voltage, like DC or battery level energy, or we can work with high AC power. For example, if we are working with thermal process, it's in order to run all these applications. So we have to be safe at the moment of working directly inside in this case, an environment that potentially could be hazard if we don't take the correct precautions during our work on mechatronics. This safety talk is basically focused on two types of systems. The first one is electrical systems, and the other one is industrial robotics. In the sense of industrial robotics is because it's the most representative mechatronic system, and many factories right now are running under ultra automation, hyper automation process that requires the presence of robotics for advanced and fast manufacturing, packaging, and multiple tasks that we could imagine. We need robotics, robotic manipulators on all its different kinds. And so this will be our today focus in that sense. All right, let's give some initial ideas on safety. First of all, is mandatory for the correct execution and performance of experiment and industrial operations. Here we see two examples. For example, here there is the robotic manipulator. As you can see here, the robotic manipulator is inside a cage in a control environment. This is like a lab environment, like like we could find in our use-immersed mechatronic labs with sensors, actuators, uh, industrial components. But if you observe, the robotic system is uh, protected by some fence or some mm, yeah, some covering in this case. Mm, this is because the robotic system, even if this is this small one arm, uh, could be harmful if we don't manipulate correct, or if something goes wrong, that could make that an accident happen. So in that sense, everything is contained inside these walls. Also, if we go to more complex system, like for example, this is petrochemical systems, safety is much more important in the sense that we're working with very flammable fluids, and any changes on either pressure, temperature, um, oxygen, or whatever can cause a really catastrophic failure, like collapse an entire oil refinery, or basically produce some hazardous flames that, of course, uh, I mean, damage the health of people, and people is injured for some mistakes in that way. So as you can see here, everything is protected by multiple layers of uh, isolation, and in this case, these pipes, the materials are designed to be resistant to corrosion, or also electrostatic discharges. We don't want that, especially in petrochemical industry. So it's mandatory safety, either in academia and also in industry. In the United States, who decide what is safe into a working environment is the OSHA, Occupational Safety and Health Administration, that is part of the Department of Labor. For the United States, they produce the regulations of safety and are the responsible for enforcement if you are in violation of some of those safety rules. So, for example, in the case of our lab, we have, I mean, in our real lab, we have to have several, following several rules in order to make the environment as safe as possible, not only for human injuries, but for fires, short circuits, or anything that may disturb or produce something much dangerous or bigger. Mm, Okay, let's start with electrical safety. In this case, the electrical safety can cause burns, shocks, and electrocution. In this case, electrocution, of course, in many cases can lead to death. There are some recommendations when we are working with electricity. Assume that all overhead wires are energized and at level voltages. Never assume that a wire is safe to touch, even if it's down or appears to be insulated. So be careful if you see any wire. Don't try to touch and assume. And if you don't know where the power comes from, just assume that it's not, that is high voltage if you don't know where it comes. That's one of the safety rules. Never touch a fallen overhead power line called electric utility. For example, last night here in Merced, and I guess in big part of California, there is a big wind that for sure at some places can make fall some of the electrical lines. Just keep those electrical lines, stay away from that, and wait that the utility came and repair everything. This is more for high voltage. If you should be at least 3 meters away from the from these cables, especially if the cables are already lit. It means the electricity is flowing. These high voltage cables has a lot of energy that if for any reason cross through our body, of course, we're going to have a burns and a heart attack. So this is some recommendations if we are working in this case with high power electricity, which is common in mechatronic environments. So we have to be careful. Never operate electrical equipment while you are standing in water. Never repair electrical cords of equipment using unless qualified and authorized. Don't try to repair some cable, at least you are the qualified person to do it. Call qualified electrician to inspect equipment before energize it. If you are not sure about some connection or some power, better call the region of the lab, or if we are during our lab sessions, before energizing even the simplest circuit and you are not sure. You can call us as TAs and we can check for you if your connections make sense and you are not going to make like short circuit or damage any of your equipment. That's something that we don't want. So always, if you are not sure, call the regent of the TA or the qualified person. If you are working in damp locations, inspect electric cords and equipment to ensure that are in good condition, and use ground fault circuit interrupt. Always use caution when working near electricity, even if it's low power electricity. I mean, just like a small microcontroller board or something like that. We should be careful. Okay, deaths, electrocutions are 14 industrial fatalities. The National Safety Council estimates that 600 people die every year for electrical causes. Most of them involve low voltage, 600 volts or less. A common operation voltage for an electrical motor is 480 volts, 240, 120. So just be careful, especially in the industrial environment. Okay, so this is a scale of danger on electricity. Even a small nightlight with 50 milliamperes could be really, really bad for you. Even this really small of current. If we check the graph, here we can see like how we can how the risk is possible. For example, if we perceive the electricity, I mean, if we touch something and we feel like this electrical touch, it only requires 0.5 to 1.5 milliamperes, muscle contractions, pain, let go threshold, respiratory paralysis, ventricular fibrillation. And you can see that even a simple Christmas light could be really, I mean, if we are not careful, could be dangerous. So if we go through a heater or some, I mean, this is just in scale of something that we can find in our homes. And even we can have organ burns or heart paralysis. So you can imagine what happened in an industrial environment with high power motors or more complex equipment that requires tons of energy. So please be careful when we work with electricity, even at small amounts, even with some safe system like a microcontroller or something. Just be careful. Okay, some causes for electrical accidents. Unsafety acts, we know better, but intentionally we do something unsafe. or we don't know better those safety rules, so we should be careful. Unsafe equipment, hazardous environment. Um, this is quite complicated sometimes, especially in some really tough applications like oil rigs or places where, or I mean, but workshops with not all the electrical certifications. We could have like really unsafe environments, or if our equipment has mm, broken insulations, or has some bad contacts, as we are going to see on some of the next slides. So it's really easy to go through electrical accidents, so it's better to be careful. Okay, some another acts, failure to de-energize, lockout, tag out hazards during maintenance, repair, or inspections. Um, Especially if you work with high energy systems like huge capacitors, banks, or industrial machinery. Those big equipments tend to accumulate energy, and that accumulate energy, for example, if it's a big capacitor, can be mortal to us. So before working with any equipment, we have to discharge, but really discharge all the electrical components of our system. That's something mandatory. Using of defective and unsafe tools, use of tools or equipment close to energized parts, not draining off stored energy in capacitors, removing the third pin on a 3-pin outlet. So basically we are removing the possibility of grounding to that cable or that equipment. And if we remove that, for example, in the case of a computer, we may put in risk our laptop or smartphone. I mean, maybe more in case of laptop, because we're not giving a way to discharge some electricity, some undesired effects uh, for our tool, and basically will be burned or severely damaged. So that don't do that. Overloading outlets with too many appliances. Um, I guess somehow all of us fail in this sense, because we have like just one outlet and then we put some splitters and more splitters. So somehow all of us incur on that in some way. Use the attached electrical cord to rise or lower the equipment, like just hang out our laptops from the charger cable. Of course, never will be a good idea. Causes of unsafe equipment: loose connections, faulty isolation, improper grounding, homemade extension cords. If we're going to get an extension, it's better to buy it. Defective parts, unguarded lip parts, for example, bare conductors or exposed terminals, especially in control boards for industrial equipment. There are some connections sometimes made live without the insulation, or just a fast connection, and that's definitely no good. Metal parts of the equipment become energized when connected by plug cords. In these boards also, we could have some parts of the equipment that for high voltage or high energy elements, those can be, how can I say it? We can induce electricity or create some capacitance effect over other elements of the rack, and then we have some electricity discharge that we don't want. Line voltage to be stored on the casing of metal tools. Basically, we are doing things that are not precisely good. How we can be result injured? We can get burns from electricity, physical injuries, broken bones, falls, muscle damage, nervous system effects, fibrillation. Those are undesirable effects on our body. So according to OSHA, there are some recommendations that they give for safety, like plan your work and plan for safety, avoid wet working condition and other dangers. Using ground fault circuit interrupters, avoid overheat power lines, proper wiring connections, extension cords temporarily. I mean, just if it's really mandatory to use the power cord extension, if not, try to, I mean, if we are into industrial environment, try to build our outlets for some specific equipment. Maintain tools properly, avoid wearing items like jewelry, watch bands, bracelets, rings, keychains, necklace that might contact with exposed energized parts. We're correct protecting equipment and use also the right shoes to work with electricity. So those are some of the recommendations. In this case, the yearly recommendation is quite interesting. I remember once when I was doing my bachelor, we were working with big capacitors, and I have some metal watch wear, and by mistake I touched the capacitor terminals, and I mean, nothing happened, but my watch result was shining and then became too opaque due to the electricity that flows through the metal. So could be worse, but it's basically, I mean, we have to be careful. So using safe equipment, don't use equipment that is damaged, using equipment to the manufacturer specifications, no, never beyond that. Check cords, should be perfect, should be always in appropriate strain relief device where they enter in the enclosure. Okay, some more recommendations. What to do if we have an accident? The first thing is prevent. Don't touch the person that is energized. You can use some rod, I don't know, rubber rod, to remove the person from the electricity, something that doesn't conduct power through that element, and pull the person away from the danger. Call 911. Keep others away from being harmed. I mean, if someone already have an accident, there's no need for more people go over there. Shut the power off. In this case, go to the power breakers of your facility and shut down everything. Move victim to safety place. Necessarily first aid. Secure the area and collect data for prevent the accident occurs again. Okay, they said that more than 50 volts should be guarded. System, circuit, and equipment shall be grounded to prevent multiple issues like shocks, fire, or they protect the same equipment from damage. In this case, another recommendations like expose non-current carrying metal parts of equipment connected by cords and plug, which may be energized, shall be grounded to prevent shocks. some violations of the code, flexible cords, strain relief to prevent pull-off of being directly transmitted to joints or terminal screws. This is important. 60% of fires are caused by poor connections and faulty outlets. Conductor entering cabinets, especially if those are electrical cabinets with high voltage. Okay, so there are some examples of bad or unsafety connections. For example, here we have like broken insulation. We have like the big cord with big insulation for the 3 wires, but also the wires, the insulation of each wire is broken. So if this is like AC power 120 volts, of course we have several problems here. We can basically have a big accident just for this reason. If we have to break a cable and make a new one or fix a connection, this is not the best way to do it. Basically, it's not covered properly, just with some quick tape. And in this case, we are splitting the connection. I guess this is the power. And here we are sending, we are deviating power from the main line and make this poor cover. So that's not a good idea. The electric arc, this is a high voltage electric arc, but also we can have small electric arcs at home, just like for these 2 wires. These 2 wires could come from any device. A toaster, oven, and this small arc is that may cause the fires. So we should be careful with this type of bad connections, especially at high power. This is some examples of safety failures. In this case, the failure is evident. We remove the ground pin from this 3-pin power connector. So this is a clear violation. Here we have like tons of code violations and unsafety things. Like, for example, here the isolation is failed. Here also is the same. The power outlet splitter definitely is not in the best condition. In this case, this big cable here, you see this metal cabinet. Basically, this is a power cable that is going directly through these small spaces of this rack. This is something that we don't desire, because even if we have isolation, and in this case, as you can see, it's not really good. Okay, let me just go a little bit. Yeah, even the isolation here is not really good. The fact that high power is crossing this small space will induce or create some capacitance effects over this metal. And if we touch that metal, we can get a shock, just because this is a lot of power creating capacitance effects over here. Also, in this case, this cable is bad, is not fixed properly. Just tape to fix the cable and doesn't move. So we have like many hazards and violations just from one picture. So those are some general recommendations for electricity. Okay, this part was for electricity. Now we are going through robotics. Electricity is like the fuel that moves all the mechatronic applications, at least most of them. But robotic systems are like the standard manipulator for advanced manufacturing and mechatronic analysis and studies. Robotic systems has many good things. However, as has good things, we have to be careful in its operation. For example, most accidents with robotic systems don't occur during a normal operation. In fact, most robot accidents occur during the following times, like adjustments to the robotic system, development of the robotic system, maintenance, touch up of the robotic system while it's working, while we are programming, prototyping, repairing, setup, testing. Basically, all the times when we have to do our work as engineers is we can have an accident with a robotic system. So, I mean, maybe for the end user, if it's just the robotic system operating, if we have the right conditions, we can't reduce at maximum the risks for accident. But in this case, for us as engineers, we are in the edge of the danger. So we have to be careful in that sense. This is why we have warnings, especially with robotic systems. We should have a lot of warnings. We don't want that something bad happens, especially could be, I mean, from a small robotic manipulator to a big one that assembles, I don't know, cars into a factory. We should be really, really careful. Some safety first, like we get hurt. I mean, if we get an accident, we will be hurt, but we don't have to endanger the other ones. It costs money for the companies. And if we are on science, like we're in academia, we also have to be careful because we cannot make more progress toward our research. So we should be always be safe. Remember, if a future you tries to warn you about this test, don't listen. Some AI paradox in that sense for robotic systems. Some safety advertisement. Warning, vehicle transforms into robot. I mean, if this is the case of a transformer, but that's not the case right now. The robotic system can be everywhere. Okay, so some typical accidents with robotic manipulators. A robotic arm function erratically and struck the operator during programming. I mean, maybe we are trying a new routine, and for some reason, we make like the robot don't go in clockwise by counterclockwise sense, and the robotic system just hit us. And if the robotic system go with really slow speed, maybe we don't have so much problem. But usually robotic systems are designed to operate at high speed, and the robotic system body is built of metal and has motors and is really heavy. So by basically the mass and inertia, the hit that you could receive will be really harsh, especially if the robotic system hits you maybe in your head or your face or any part of your body, but is, I mean, could be really, really bad. A robot operator entered a robot workspace during operation. The robotic system doesn't, I mean, the robotic system fulfills some task, like pick and play task or soldering task. And it's not supposed that an operator is inside the environment of the robot. And the robot doesn't have any smartness or intelligence to said like, okay, if I'm going in this way, I see a human, I'm not going in this way, or I'm going to stop my work. No, the robotic system is programmed to perform some task, and we repeat exactly the same task again and again. It doesn't consider humans, so this is really dangerous. A fellow employee accidentally turned on a robot while maintenance worker was servicing an assembly robot. The robot arm struck the maintenance worker, so someone turned on the robot and the maintenance employee or us as engineers can be struck by by the manipulator. So again, for safeguarding in this case, the first thing right now is safety. I mean, if we run our safety every time, we are going to minimize the risk. For example, first thing, eliminate hazard, reduce hazard, provide safety devices, provide warnings, and provide safety procedures. In that case, this is really, really important for us. Try always to minimize the risk. And if you are in an industrial environment, people sometimes could be really emphatic on take a lot of safety measures. So that's one of the points. Okay, this is like one example of industrial robots. Those robots, for sure, as you can see, are really heavy. And okay, those are cooperative robotic systems. Both robots are performing a cooperative task. In this case, this robotic manipulator holds some crystal body, and the other one has like a small drill, and they are like the one holds and the other one drills. That's an example of cooperative. A typical robotic system, this is according to International Robotic Association and ISO norms and standards, has a power supply, a controller, a mechanical unit that is composed by all the mechanical parts, gears, belts, motors. And at the end, we have the robot tool. This tool is basically the end effector of the robotic system. In this case, for example, is a drill. In this case, is like a clamp. According to the robotic system, that that clamp or that tool will be different. For example, if it's a soldering robot, will be like a soldering tool. If it's a painting robot, that will be in that case a spray dispenser, or I mean, it changed application to application. Some of them, like those, has to be in direct contact with the object or surface that they want to interact. Another ones, like the paint robots, just have to be like certain distance, certain distance far from the surface where they are going to work. So those are some examples. Something important about robotic systems in general for robotic manipulators is that all the robotic systems has something that we call the robotic system workspace or work envelope. This is like a serial robotic manipulator, which is like the standard one in many applications. If you see this semicircle here that looks like a Pac-Man, we have here that this is our maximum. I mean, if we look from the top, we have this maximum operational rank for the robotic system. For safety, we have to restrict that space, as you can see here. The same if we are moving, this is from top view and this is from lateral view, we have to constrain the space. And the operational environment, of course, will be smaller. I mean, we have like a big space where we can work, but we should reduce the amount of operative space according to application that we have. So in that sense, we are safe that, for example, if this is my maximum envelope and I put some warnings that no one can cross this part, but our operation rank is just this small black part. And for some reason, there is some obstacle between, for example, here, we have some restricted area where our robot cannot move further from this. So we have to constrain in order to be safe. Maybe it could sound like we are not using or taking advantage of all the capabilities or space of the robot, but terms of safety, it could be a really good option, especially if our task is really, really specific. Some source of hazards for robotic system. The expected hazard to matching to humans can be expected with several additional variations that follows. First of all, human error. Of course, in this case, could be like a bad programming of the robotic system controller or trajectory path planning. If we if we don't code properly, for sure we are going to perform an error. We will have error. We have to consider that a robotic system is complex in this case, and we have to have a really good understanding about all the movement of the robot before programming. One way to do that is understanding which is our operational ranks. If we are directly, from the developing stage, that's one of the ideas of using advanced simulation models. We can know in advance how much we can move or we want to move with the robotic system, and we can get familiar with all the models and restrictions. Some robotic systems, are automatically programmed to perform some task, and other robots basically are driven by a teacher or human teacher that tells the robotic system to learn some trajectory. For example, if it's a really specific task and we don't want to code like everything step by step, we can use human profiles and make the robotic system learns. That's one of the ways. In that sense, we have to be careful because as we move the robotic system, we can have some errors and our robotic system can harm the operator. So that could be complicated. Control errors. These control errors are quite interesting in the sense that not necessarily is because our control logic is bad or our controller doesn't work. It's because like for some random reason, some internal component inside the controller breaks, like let's see, I don't know.
Hi, good morning. Can you get the meat burrito?
Sorry?
Thank you.
Sorry. Okay.
Oh, sorry, that was my bad. I didn't know I was unmuted.
Okay, that's okay. If something fails, of course we will have problems. We have problems, or for example, one of the sensors is broken or start to or send failures. So our control is not going to be okay because we are under fault, under fault status. One of the things, that we are introducing digital twin for first time in this course is that using digital twins, we can simulate these bad or worst case scenarios where we can know what we have to do or what our controller can do in the sense when these undesired events happen. And we don't have to harm anyone because we are on a simulation virtual replica. So that's a really good thing about this digital transformation. We can perform a lot of evaluation before running directly on the real life. And in this case, for safety, it's perfect because we don't have to, we don't have to wait that things happen in real life. We can predict multiple scenarios and see what should be the best way to proceed. Another problem for robotic systems, like unauthorized access, someone that go inside the cage, or someone that puts in the middle of the safety zone, mechanical failures. If some gear is broken by just multiple actuation, it's going to be, there's going to be fatigue. I mean, if we use digital twins in a more advanced way, we can predict this fatigue using some data-driven techniques like machine learning or deep learning techniques. We can go into that way. Environmental sources, electromagnetic interference. The electromagnetic interference, right now we don't have, I mean, there is a lot of work behind that. I mean, if some high energy source produce a lot of radiation or electromagnetic radiation in this case, devices are covered with some materials that doesn't emit so much radiation, or our devices, more sensitive ones, are more robust. The design is more robust in order to resist any electromagnetic variation. However, in the case of the robotic system, uh, at in the industrial case is super robust, but could happen. Or also, I don't know if there is some leaking or there is some high temperature condition or something harsh that affects everything. So those things are also unpredictable, but we have to minimize all those risks. Power systems, many robotic systems use electricity as main uh, fuel and main energy to perform motion. But once our system requires more power, like, I don't know, move big pieces or something, uh, pneumatic and hydraulic actuators are required for our systems. In that sense, it means that we are not only dealing with electricity, we are dealing with pneumatic or hydraulic. That also has its own challenges and risk. For example, if we are using like air, and if we are using air to move some pneumatic pieces, and we can have some failures on the air compressor, or if it's super high compressed air and we have some leaks on the pneumatic piece, pneumatic actuators, we will have some, we'll have in that sense some new challenges. And if it's oil, it's worse because it can burn, and if it burns, it's also bad for us. So also, if we have like compressed piston and then we release the energy and we didn't realize about that, the piston just can release suddenly and it has a lot of force and it can hit us. So that's another safety risk. Improper installation, I mean, if we didn't fix correctly a robot, we didn't install a cage, we make like weak connections, there's a lot of problems that we could have. There are some recommendations from International Robotic Association. The first one is put the robotic system in a cage. It's the first one and the most important one. And only has one access to that cage, as you can see here, and always de-energize all the robotic system, removing all the potential kinetic and potential energies that the manipulator could have, in order that once you operate the robotic system, you don't have any risk that the robot suddenly just move and hits you while you are doing some maintenance or while you are making some review of some components. So that's another important thing. Power and force limitations. As much as possible, try to reduce the robot mass and inertia. I mean, a robotic system can produce a lot of inertia, but not necessarily always. We don't need to use all those inertia to move from point A to point B. So we have to reduce that one. Eliminating pinch points. For example, in this case, this pinch point could be, for example, like, I don't know, like that drilling tool that we see before. And that drilling tool, if it hits to our hand and it goes with a lot of energy, that will be a really serious injury. But if we cannot, I mean, we need the drilling tool. Basically, we can just rotate the direction of the tool. I mean, in order that if for any reason the robotic system hit us, there's no pinch point that make, I mean, of course, we probably could have some injury, but it's not going to be as bad as if this is a pinch point. Modify robot posture, avoiding affected sensitive areas. Try always to make everything thinking in, make it safe as much as possible. This is some safe robotic facilities. For example, this robotic system is moving cages. I guess this is like food factory. You see, they have like 3 robotic manipulators. The robotic manipulators take the baskets to this line, but the robotic systems are in a cage where no one can go inside just for except by this regulation by these inputs spots. Same here, we have the cages, the basket inside the cage, the robotic system, everything is contained here. Also, in this case, you see these alarms here. So those are also for safety of the tool and safety of the people. Only one access. And the robotic system has enough space to deal with this task, as well as in this case, the baskets that are over here. So everything should be really good planned before dealing with, in this case, a robotic application. Okay, some robotic safety rules. ISO 10218-1, robotic and robotic devices, safety requirements for industrial robots. OSHA Section 4, Chapter 4, Industrial Robots and Robotic System Safety. Those are some of the standards that could be used for robotic manipulators. Of course, from country to country, these regulations are going to change. But in this case, for the US, those are the ones that we should follow in order to develop a safe robotic application. Of course, is okay. We have a question here. What kind of application do these robotic arms has in industry? Okay, one application could be soldering. I mean, like soldering in an assembly line of cars. Another one could be pick and place task, like move some components from one point to another point. This is another one. Also, I mean, pick and place is like one of the most popular tasks for robotic systems. Also, I mean, manipulate some hazardous materials, like for example, if you are dealing with vaccines or some contagious disease, there are some robots that can handle a set of these strains and move from different places. Paint is another application. I mean, there are some specific places that are really difficult to reach for human to make paint. That could be one way. Another application. Okay, could be like submarine exploration. I mean, you cannot, if you are too deep in the ocean, you cannot use a robotic arm to grab some samples on the bottom of the sea. So you have to use that. You have to use that robotic system. Let's say here, robotic. Okay, of course, there are some fun applications. This is from KUKA, one of the top robotic manipulator manufacturers in the world. This case is like for example, let's see this one. You see in this case, it's like a fun application. The robotic system is too soft to perform like glass singing. This is one way. Basically, it's replicating this guy movements just by visual inspection.
You didn't open your sound when you.
Oh, sorry.
When you share, you can reshare and click the sound on.
Okay, let me just.
Yeah. So the Zoom should put the default is on. Then you need to click to make the. Right.
Okay. Checking.
On the bottom, there are two boxes you should check when you share. I think everybody's tired, so they deserve some entertainment. So it's 100. It's like over 100 minutes, like 110 minutes. Continuous input of linguistic materials. Do you know how to do it?
I'm checking.
You click share screen in the bottom. There are two check boxes about sharing the audio. So and then when you play your video on your computer, do you see that?
Yeah, I got it.
Okay, now, okay, great.
Okay, now you hear? Can you hear right now?
Yes, we can.
Okay.
This is beautiful. Thank you. I didn't know that. But you need to ask how many glasses he smashed before he can do that. All right?
Of course,
So
during the training.
they show the best for you as if they never smashed any glasses. That's not true. You see this smashed one. Oh, no, not a robot. It's a guy. Oh.
Okay, guy 1, robot 0.
That's cool. Very nice. Thank you. I never watched this before. KUKA is very famous. KUKA has a branch office in northern Modesto. What is the small town? What's the small town in the north of Modesto?
No, Stockton? No.
Forgot. But anyway, the branch head visited our lab. They are doing for the warehouse robots. And so I may send you guys there for internship. So they are like a branch. They are also a company under KUKA. Okay. So interesting. So it's not, KUKA is not far from us actually. So just 40 minutes drive north. Yeah. Good. Thank you.
Do you have any other more questions, guys? Maybe we can watch final. I guess this is more popular. Again, man versus machine. Table tennis. Interesting, dealing with multiple balls at the same time. So I guess this is the lab for today. If you have any questions, please go through. If not, you have the lab assignment already submitted on the CAT courses. Any questions, you can just sign me by email if you have any questions, or directly message through CAT courses. Any of those could be really good. So Any questions? For lab 1, free format. There's no, I mean, the IEEE format is from lab 2. For this lab, is free.
I have a question actually.
Yes.
For it says like the 5 guidelines. Can they just be like any of the points stated through this lab safety handout? Well, 2 of them. 3 have to be through other sources, right?
You have to propose the 5, and I mean those 5 could be 2 from you and 3 from other sources. I mean, should be different from that we said on the class. That's the main point.
Okay, got it. Thank you.
Okay. Yes, lab 1 is already published on CAT courses. You should receive the notification. I mean, was posted last night on the homework section laboratory. Yeah, it's already published. You can see here. Everything. Yeah, that's the same one. Deadline is February 5, so you have plenty of time to finish it. All right. Any other question? Okay, so I guess we can finish for today. Thanks for your time and patience with this first lab session, and see you next week on the lab. Remember, the lab will be available on Sunday, so you can watch the video tutorial on Sunday, from Sunday. So see you next week or on office hour, whatever it comes first. Right. See you guys. Have a good rest of the week.
Oh, hi. I answered late today, like around 9:10. I was wondering if I missed the attendance.
No.
Oh, okay. Awesome. And sorry for the interruption earlier.
No problem.
Have a nice day.
Okay, have a nice day.
Excuse me?
Yes.
Jairo?
Yes.
Can you hear me?
Yes, I can hear you.
Okay. So lecture is from 1 to 2:30, not...
No, 1 to 2:30 is office hour. 2:30 to 3:45 is lecture.
Okay, all right. Thank you. I appreciate it.
Sure. Okay. Have a good one.
You too.
Okay.